Hey everyone. So the notes that you're going to do today is half on something called the kinetic molecular theory, and the other half is on something called the combined gas law. So the kinetic molecular theory are just ideas about gases that you need to know. Remember, I said that this unit is on gas laws, so we're mostly focusing on gases. Yesterday, we went over some ideas you should know about solids and liquids. The rest of this unit focus on gases. So the kinetic molecular theory will state 6 ideas about gases that you should know. And then the combined gas law is an equation that we are going to use in class. Okay, but before we talk about the kinetic molecular theory, I want to show you the simulation. So in this simulation right here, we have this box, and this box, I can change the size of the box. So this is about volume. Changing the size of the box is changing the volume. Here I have a smaller volume, and then now I have a larger volume. That can also control the temperature. Well, the first thing I need to do for this box is to add some particles. So I'm going to pump in some air. Well, this is just a gas. And you can see that the gas right now is filling up the box, okay? The particles are constantly bumping into the walls and into each other. Now, the amount that they're bumping into the walls has to do with pressure. So the pressure is about the collisions. How many times are they colliding? The more the particles collide with the walls, the higher the pressure. So let's say I make this box smaller. Because I made the box smaller, the particles are going to start hitting each other more, and they're also going to hit the box more. So that's why you could see that the pressure increase. What you may have also noticed is that the temperature really increased, and that's because the number of collisions has to do with the temperature. The more they collide, the higher the temperature. And then if I made the box smaller, if I made the box bigger again, you notice that the pressure went down. The temperature changed a little bit. It got a little bit lower, but nothing significant. But here's the thing that I could do. I could add heat to this scenario. Heat is going to make the particles, as you see, move faster. Or I could remove heat. I could make it colder. And what you'll notice is that as I make it colder, the particles are not colliding with each other as much. And then I can try to go all the way down. And notice that the particles are moving slower and slower and slower. So they're losing energy as I'm doing this. And then eventually, I'm going to get to something called absolute zero, which if you notice the temperature, absolute zero is 0K. The K is the way we measure temperature. In chemistry, we can use Celsius or K, which is Kelvin. In all the problems that you're going to do, we're going to use Kelvin, but what you'll hopefully notice is that at 0 degree, 0K, 0 Kelvin, the particles have stopped moving, and that is something called absolute zero. Absolute zero is when all particles stop moving. All right, so for the kinetic molecular theory, here are some of the pieces that you need to know for the kinetic molecular theory. Those gases can be compressed, and compressed means that they can be squeezed tighter and tighter. Now, if you think back to that simulation, that box, I could make this box smaller, and that's compressing it by making the box smaller, and that's because there's space between the particles, and if there's space between the pieces, then I can close that box to make it smaller. But let's say I have a solid, like a calculator. You can't squeeze that, really, to make it smaller, so those particles cannot be compressed. Gases can be compressed. The movement of the gases are constant and they're random. So they're always going to move unless they're at the 0 Kelvin, and they're random, so they're unpredictable. Every collision has the same amount of energy. No one collision has a higher amount of energy than another. The gases will also expand to take the shape and volume of the container. So keep in mind in that simulation, when I made the box bigger, the gases expanded outwards. If I made the box smaller, then the gases were confined to a smaller space. The fifth thing is that gases exert pressure, and the way that they have pressure, remember I said pressure has to do with the collisions. So every time they collide with the walls and each other, that is pressure. The more they collide, the more they hit, the more pressure we have. The last thing is that they typically have low density. Now we took that in our notes, but just make sure that you understand gases in general have a low density. That's under normal conditions. We're always going to deal in chemistry pretty much with normal conditions though. Okay, so the question is, how do you think energy and temperature are related? Take a moment to try to jot some down ideas. And what you hopefully wrote down and hopefully what you've realized is that the higher the temperature, the more energy we have, right? So increased energy means an increase in temperature. And then if I decrease the energy, then I decrease temperature. And I can decrease the temperature enough that I have zero energy, which is that 0 Kelvin, which remember is this moment when the particles have no energy because it's 0 Kelvin, and so they stop moving. So in chemistry, we call that absolute zero. So absolute zero is 0 Kelvin, or you can also think of it as negative 273 degrees Celsius, and that's when the particles absolutely stop moving. 0 Kelvin is not easy to replicate. In a lab environment, it is very hard to get the area to 0 Kelvin because it's such a cold temperature, and because the particles have stopped moving at that point. In a lab, they were able to get pretty close to 0 Kelvin, but I don't know if currently any lab has actually been able to reach absolute zero. So really right now, it's just a theory that absolute zero means the particles will stop moving. Okay, you need all this information in your notes. The 3 variables that are important right now are pressure, volume, and temperature. So you can describe a gas based on its pressure, which is the number of collisions. And the units we use to measure this is something called ATM atmosphere, the millimeters of mercury, the torr, or the kilopascals. So if you see a number that's 760 torr, well, that means that's the pressure, right? The volume is the amount of space something takes up, and we're always going to measure that in liters. This note right here, if you're given milliliters, then you're going to convert and know that every 1 liter is 1,000 milliliters. The temperature is how much energy something has. Cold temperature, low energy, high temperature, high energy. We're always going to measure this in Kelvin. So instead of using Celsius, what you should do is take Celsius and add 273, and that's how you'll get Kelvin. Your chart also has areas for moles and STP. I want you to skip that right now. Don't mark it out. We're just not going to do it right now. Okay. So now we're going to move on to the other part of the notes, which is on the combined gas law, and this is where you need a calculator. So take a moment to copy the equation. The P in the equation stands for pressure. Now remember in your notes, you said you took notes that pressure can be measured in atmosphere, torr, millimeters of mercury, or kPa. And when you're doing these problems, there's P here and this pressure over here as well, P2. The only thing that has to be true is that let's say you start with a pressure in atmosphere, then your pressure on the right-hand side should also be in atmosphere. So they should just match up. V stands for volume. Your volume has to be in liters. So let's say you know 1,000 milliliters is 1 liter. That's an absolute for sure thing that you should know. Let's say that you have 3,250 milliliters. Well, how do you convert to liters? You just divide by 1,000 and you get 3.250. I don't know about all the lines. Sorry, y'all. 3.250 liters. Okay, so that's how you convert from milliliters to liters. Let's say that you have the T. This is going to be your temperature. Temperature is measured in something called Kelvin. But let's say that your temperature is given to you in Celsius, like 15 degrees Celsius. Well, you just add 273, and that's how you're going to get 288 Kelvin, right? So the P, V, and the T on the right-hand side of the equation is still pressure, volume, temperature. What's different, though, are the numbers 1 and the numbers 2. 1 represents the original condition. So originally, what is the pressure, volume, and temperature? The 2 is going to represent the changed conditions. So maybe the pressure changes, maybe the volume changes, maybe the temperature changes, or maybe all three change. Well, if that's the case, then that's your 2, your changed conditions. Now we're going to use these in a math problem. Take a moment to read the first problem. Here are the pieces you need to know because of the equation P1, V1, T1, P2, V2, T2, right? 1 is the original conditions. Well, it says the balloon is 30.0 liters, so that's volume. It is 40 degrees Celsius, so that's temperature. But I need to add 273 to get it in Kelvin, so this is 313 Kelvin. The 153 kPa is my pressure. What volume will the balloon have? Which means you don't know the volume. You don't know the changed volume. If the temperature increased to 50 degrees Celsius, if it increased, that means it changed. So 50 degrees Celsius is my T2. But in Kelvin, I need to add 273 to get 323 Kelvin. And the pressure decreased to 110 kPa. So that's 110 kPa. Now that I know these pieces, I'm going to take the parts and I'm going to plug it into my equation. P1 being 153, V1 being 30.0, T1 being 313, P2 being 110, V2 I don't know, so I'm just going to write V2, divided by T2, which is 323K. Now the way that you're going to solve for V2 is you're going to cross multiply. So cross multiply means things that are diagonal to each other should be multiplied. So 323 multiplied by 30, multiply by 153, that gets you a really long number, 1482570. Now that I have that, I'm going to set it equal to, and I'm going to keep cross multiplying. 313 times the 110 times V2, and that's going to get me 34430, and then I still have V2. I need to solve for V2 now, and I can only solve by dividing both sides by 34430. And then if you do that in your calculator, you get a V2 of 43.1. Now the unit, if this is volume, the unit has to be in liters. Okay, so this is all the math for it. You don't absolutely always have to show every single thing. This stuff, when I plan out, you don't have to always show it. It's just helpful. This setup, though, for your math, you absolutely have to show. You also absolutely have to show your answer, but you don't have to show all the math in between in your calculator. Okay, we're going to read the next problem. Take a moment to read it. Okay, here's what the equation is going to look like in the end, but here's how I figured out how the equation should be set up. It says the volume of a tire is 2520 milliliters. So that's my first volume. But that's in milliliters, not liters, so I divide by 1,000, and I get 2.520 liters, which is how this number came to be in the setup. It's at 15 degrees Celsius, which is in Celsius, not Kelvin, so I add 273, and I get 288 Kelvin. Sorry about the random lines that are being drawn. There's the 288 Kelvin. The ATM pressure is 2.98 atmospheres. What temperature will the tire be? Which means you don't know T2. If the volume is now 20.1 liters, that's already in liters, so I don't need to convert. The pressure is 5.63 atmosphere. So taking all these pieces and setting it up and plugging it into the equation looks like what I have already typed right here. Okay, so now for solving, again, cross multiply. If you don't need to show all the steps and you understand what you're doing, just get me the answer. What if I cross multiply? I do 288 times 5.63 times 20.1. That gets me 32590.944. Okay, equal, and I keep cross multiplying, T2 times 2.98 times 2.520. That gets me 7.5096 times T2. Need to get T2 by itself. So to get T2 by itself, I'm going to divide both sides by 7.5096. And if you do all the math correctly in your calculator, and please be sure you're trying this yourself in your calculator, you should get an answer of 4,340. This is temperature, which means the unit has to be in Kelvin. Okay, for the next question, here is the setup, but then let's make sure you understand how I got that setup. It says a gas at 155 kPa, that's the pressure. And 25 degrees Celsius, that's the temperature, but add 273 because it needs to be in Kelvin. This is now 298 Kelvin. Doesn't give me the first volume, so I'm just going to keep reading. It says if the volume of the gas decreases, which means there's been a change, if it decreases to 3,425 milliliters, that's my second volume, not my first. But notice this is in milliliters, so divide by 1,000 to get it in liters, 3.425 liters. The pressure increases to 605 kPa. And the temperature changed to 345 K. This is already in Kelvin, so I don't need to add 273 to it. What was the original volume? So here's how it's different. It's asking you for the V1, the original volume. All of this work gets you this setup, which you have to be able to show. Okay, solving for it, I cross multiply. 298 times 605 times 3.425, that gets you 617,493.25 equal to, I'm going to keep cross multiplying, 345 times 155 times V1. That gets me 53475 times V1. I need to get V1 by itself, so I divide both sides by 5. I need to multiply both sides by 53475, and I get a V1 of 11.5, and the unit for that is liters. Okay, I'm going to quickly show you the other answers. You should try it out yourself and make sure you can do the math and the setup correctly. Here's 4, here's 5, here's 6, here's 7.